So let's look at output impedance. PMOS LDO. So the same LDO I will take and we will derive the equation for output impedance. Okay, the two pole model. We'll just consider the two pole model and we'll so now I am just changing this to from GM2 to I am changing it to GM1. And I will call this one as GM2 and I will define this pole as omega P1 and the output pole as omega P2. So this is your minus plus let's have a beta factor R1 R2 okay and R load and C out. You have RO1 and CO1 VDD. And the pole here is omega P2. Okay. Okay, so let me make RO2 equal to R1 plus R2 in parallel with RO2 of that transistor parallel with R load. So I have combined everything in one resistor. Okay. So Z out. Z out should be what? V out over I out. Instead of V out, let me call it V test over I test. When I say V test, you are applying a source here called V test. Okay. So we need to find V test over I test. Can anybody do quickly? 1 by GM2. Why GM2? What is the DC resistance? Z out at DC. Wait. Okay. I don't want you guys confused with RO2 and that. So RO2 is defined as output resistance or RDS of your MOSFET, and let's call the overall equivalent output resistance as R out. So without feedback, R out is output impedance is R out DC. So which means DC output impedance, which I will say Z out DC equal to R out over 1 plus beta N out. Correct? What is A naught? Into Okay. So, this is your overall gain. Now, what happens if we have a capacitor? What will happen to your transfer function? So, your Z out will become R out, not R out, sorry. Because R out is DC only, so you have to consider that pole also. So, Z out equal to your output is 1 over which makes it R out over R out S, correct, divided by 1 plus beta AS. Is this correct? So, once you start considering the cap, so the impedance looking at this will be R out parallel C out, and that is what you get, R out over 1 plus R out C out S when you have R and C in parallel, divided by beta and overall loop gain transfer function. So, what is the loop gain transfer function? Hmm? 1 plus so what is AS? Beta A naught over 1 plus omega, sorry, S over omega P1 into S over 1 plus S over omega P2, and this is nothing but S over omega P2. So, what will you get if you solve it? So, this guy will cancel out, omega P1, omega P2, wait, there is a 1 plus term also. So, now you have 1 plus S over omega P1 into 1 plus S over omega P2 divided by okay. So, this will go away. What you have, R out over So we have 2 poles and 1 0. Now we have to simplify this and find where the poles are. So the denominator looks, if you break the loop, it will become a quadratic equation and it will complicate the things. So how can I simplify this? So consider a compensated loop. Can I consider that, say that before UGB you will have only one pole? The second pole will be outside UGB. So which means for omega less than omega UGB, which pole will go away? Omega P2. Over correct. I can write it 1 plus okay. So what is happening here? If you put S is equal to 0, what is the DC output resistance? R out over 1 plus A beta, which we already have, which means, so we already verified that Z out DC is R out over. So if you substitute S equal to 0, you will get the same thing. Now for S greater than 0, what would happen? Draw the Bode plot. What is the DC? So if this is your Z out as magnitude, R out over, I will approximate it to R out over beta A naught. Beta A naught is much larger than 1. What would happen? Let me move it down so that we have some space. I will start from here. So I have a 0 at lower frequency, correct? So the pole, the first pole, or I will say your dominant pole, omega P1, now has converted into a 0 for impedance. So if this is omega P1, how long it will go for? So where is that pole? Pole is at UGB, okay. So this is beta A naught omega P1 and it flattens out, correct. Now we have to consider the second pole, okay. So let us say your second pole hits here after UGB, then it will start going down. Let me change the color. Okay. So what does it mean? Where will it go? What is the maximum? Okay. Maximum will be R out. So now intuitively if you look at this circuit, what is happening? Which means if you make a this pole dominant, if you make this pole dominant omega p1, then what would happen? After UGB, this will behave like a short 0. So, the impedance looking into this will be nothing but R out of this parallel R1 plus R2 parallel R load, and that is what happening at UGB. Okay. Before the second pole hits. When the second pole hits, this capacitor will come into picture and it will start creating a short impedance path. Okay. And then it will be driven by simply your second pole in that case, and it will start going with minus 20 dB, and not think about very high frequency. Very high frequency, this capacitor will act like a short to ground, so your impedance will be 0. Okay, that is what is happening. See, if I want to achieve a very low impedance at all the frequencies, which pole should I make dominant? Output pole. Okay, so that is a benefit of having a, so I mean there are a lot of benefits of having output pole as dominant. One, obviously your PSRR, when we talk about that we will look at, but it also helps in your output impedance, and if output so DC impedance will not change obviously, and we know the DC impedance is nothing but your load regulation, correct, delta V out over delta I out, that is what we defined as load regulation. So, DC regulation may not change, but your AC regulation is changing, which means your load transient will improve. So, making output pole dominant will always have a better load transient compared to making this error amplifier output pole dominant, correct. So, if you have omega p2 dominant, then this is so since pole, the first pole is already at outside UGB, so 0 will be outside UGB. So, when the 0 hits, what will happen? It will flatten out, and then so it will keep going. Let me draw from here. So, we are just swapping the poles, huh? So, omega p1 becomes omega p2, and this becomes beta I naught omega p2, and this becomes omega p1. Then it will flatten out here, and then your pole will come at some gain, and then again. So, it is only improving, there is no 0 as such, it is not rising, your gain is not rising in that case. So, you can completely ignore the effect of your pole and 0 due to second or non-dominant pole. So, your output impedance will always get better. You require a very large gap, but there is a benefit of having that large gap, that is what I am saying. It will require, that is the reason we do not do this actually. Okay, so there is a trade off, either you put a very large gap or you live with your poor transient response during that. So, there is a always trade off, you have to decide which is more important in your case. If you are looking up for a very good transient response, then you do not have any option but to make the output pole dominant. Okay. But if you put a very large cap and still your this pole is dominant, then that may not help actually. If you put a very large cap, let us say, and still your omega p1 is dominant, then increasing that cap may not help in transient much in that case. Okay. So, it will only help if you make the output pole dominant. Yeah, you can always do that. So, it will reduce the basically output cap size by some extent. So I mean it all depends actually how, but it will always come at the cost of something. So in that case you have to burn some extra current in your buffer, okay, because ideally you would like to have GM as large as possible so that your that pole is pushed at very high frequency. So making GM large means you have to burn some current there. So there is a trade-off between your bandwidth, power, everything, transient response. So and that's what we try to do. I mean that's why a lot of research is going on this. How we can design a very fast transient with a very low, with a high bandwidth and with a very low IQ current. So that's a lot of work is going on actually. But theoretically, if you look at this, there is a trade-off, and you want to just break that trade-off and come up with some innovative topologies so you can achieve a better response with the lower IQ. And that's how we define the figure of merit. We look at the total number of cap you are using, then total power you are consuming, and how much is your settling time and undershoot overshoot in terms of transient, and what is your PSRR. All these you combine to come up with a figure of merit for these regulators. Okay. So improving the transient response means you need to increase the bandwidth obviously. Okay. So increasing the bandwidth means if you make a omega p1 dominant, then the only way to improve the transient response is to push the bandwidth higher. Okay. So this region, this particular region, you want to push this peaking at higher and higher frequency to improve the transient response. Okay. So which means if I want to improve the transient response with omega p1 dominant, I have to increase the bandwidth. No, loop DC gain increasing does not mean that you will increase the bandwidth. Okay. I mean, if you let's say you increase the RO1, that will increase your DC gain, but that will push your pole at a even lower frequency. Yeah. So just increasing the DC gain will not increase your bandwidth until unless you increase the GM factor also. Okay. So if you increase the gain, I mean you can look at it. If you increase the beta A naught, you will see your UGB will fall at the same location because your omega p1 will also move in, and it will just coincide with the same graph ultimately. Okay, it will be like this. If you just increase the gain, because increasing the gain you can do it by reducing the current also. I mean you can simply increase the R out, that's it. So if you increase the arbitrarily just increase the R out, that does not mean that you will increase, it will increase the bandwidth. It will not do anything unless you increase the GM also. So if you increase the GM and R out both, then you get a higher gain and higher bandwidth. That's why you have defined gain bandwidth product. Other will just define gain. Why do we care about the bandwidth product in that case? So your gain bandwidth product remains constant here, and that's why you won't get any benefit in terms of bandwidth, but you will get a benefit in terms of only DC gain. So if you care about the accuracy, obviously that will help, but that may not help in transient response. Okay, so you have to increase the bandwidth, which will come at the cost of your current, obviously. So and that's what you try to always reduce, build a high gain bandwidth amplifier with reduced current. But if you make the omega p2 dominant, then in terms of transient response, your bandwidth may not matter that much, because if you keep increasing the C, you are pushing your pole in and in, which effectively is reduced. Let us say your gain is constant, but pole is moving inside. So, your UGB is reducing, but at the same time your output impedance is also reducing. So, that is why your in that case, even if you make a lower bandwidth, your transient response will be better compared to other case if you make the output pole down, because your capacitor will itself will absorb everything, all the transient. Okay. So, we know that DC impedance is nothing but your load regulation, which is defined by your delta V out or delta I out, and that is basically universally proportional to your loop gain, DC loop gain. So, which means if I want to improve my load regulation, I have to increase the loop gain or DC loop gain. And so, and if you look at the high frequency component of this, so we have a 0 which is corresponding to the dominant pole if it is appearing at the output of your error amplifier or first stage, and that will degrade your output impedance at higher frequencies, and it will make worse around UGB. So, which means my load transient will degrade due to this 0. So, if I want to improve my load transient and keep my dominant pole at the output of your error amplifier, then I have to increase the bandwidth. Okay, so that I can so I am mainly interested in this region, the flat region. So, if I extend this flat region, I will get a better transient response, or another option is you make your dominant pole at the output. So, we will do the same thing, we will derive the same transfer function, but for PSRR we will make the input at VDD, and we will do the same small signal analysis, and we will see what transfer function we get. So, we'll all we have to do, we have to derive the, so it is a line regulation basically. PSRR is a line regulation for AC. So, we have to derive V out over VDDS, that is it, V out S over VDDS, that transfer function in the closed loop, and we will see where poles and zeros are and what improves your PSRR, what degrades your PSRR, and more or less you will get the similar thing what you are seeing for the impedance case. You will get a 0 if you make the first pole dominant, and if you make the output pole dominant, you won't see that 0. So, that is why I said if you make the output pole dominant, it not only helps in improving your transient response, but your PSRR also, because any AC at the output will be absorbed by that capacitor. So, that is always going to help, putting a, I mean increasing that cap output, making it dominant will help in all the cases. Increases in what case?
Like making the output pole dominant.
No, that won't increase, that will decrease.
Output pole dominant by increasing the capacitance.
Yeah.
So R out DC will not change. DC R.
Yeah, why DCR out will change? It is only capacitor you are increasing.
Oh, but in terms of frequency response it will.
Yeah, I mean why DC will change if you are changing the cap? I can make this capacitor anything. If you make it infinite, even then your R out is same. R out is not going to change. It will affect only Z out. So, your DC R out, I mean for DC a capacitor is open. So, it does not matter that it is a 1 picofarad or 1 farad. At DC it is open. So, the value of cap will not affect your DC resistance.